Yeah, so I asked because the coding section of the workshop is designed for um, everyone, so from beginners to advanced, to be able to tackle it at their own pace. So when we get to that part, you can either follow along with me or you can make a copy and just um, apply it yourself. So that's what I was wondering. And then, how many of you have experience in AI or machine learning theory before coming to this workshop? Okay, cool. That's like my favorite part. So we'll be going over that during the workshop as well. So hopefully, by the end of the workshop, you guys will all raise your hands in Python experience and AI and machine learning theory experience. So let's get started. Okay, can everyone see my screen?
It's coming through, yeah.
Yes.
Okay, perfect. So throughout the workshop, as I mentioned earlier, we're going to go over um, an intro of AI and ML, an overview of different types of ML, and I'm calling it AI and ML, but let me just tell you what it stands for. So AI stands for artificial intelligence, and ML stands for machine learning. And one of the most common questions I get asked is what's the difference between AI and ML? So we'll also be going over that in the workshop. And then one specific ML algorithm that we'll be focusing on is called linear regression. So we will learn about the theory behind linear regression, and also we will learn how to code it and apply it to a business concept. So first, what is AI? The definition of AI is basically when a computer is able to perform tasks that normally require human intelligence. And something I want to highlight is you can imitate human intelligence by explicitly coding what you want to do. So the most common example of this is a rule-based chatbot, where it's not actually intelligent, but because it knows the strings that you're going to put in, it is able to kind of imitate human intelligence and respond with words that match what the input is. AI can also be used in computer vision and also speech recognition and natural language processing. So if you guys have ever used Siri or if you guys have ever used Cortana, then you were using the AI in the speech recognition and natural language processing. And AI can also be used in robotics. So I don't know if you guys have seen that one robot that was able to retrieve some shipwrecks from the bottom of the ocean that was programmed using AI algorithms. So yeah, so these are basically all the different applications of AI and how they can imitate human intelligence. So now the difference between AI and machine learning is that machine learning is basically a subset of AI. So all machine learning is AI, but not all AI is machine learning. And you may remember from the first slide where I said that AI can also be rule-based and not actually like pattern recognition. So machine learning is the part of AI that is what you would think of when somebody says AI. That's like the pattern recognition where you feed in a bunch of images and it learns from the patterns and starts predicting them or classifies them or segments them or any of that. So in machine learning, the computer learns from the patterns in the data, and you do not explicitly code what you want the computer to do. So that's kind of the difference between ML and AI. Now, within machine learning, there are a few more classifications. There's supervised learning, where every example from the data is labeled. So for example, if you were doing an image classification task with shapes, you would feed in a shape of a rectangle like this, and then you would also feed in a label with the label rectangle. Same with if you were feeding in triangles, you would feed in an image of a triangle and you would label it with the word triangle. So we will be doing supervised learning in this workshop, but there are a couple other types of learning that I'd also like to highlight. So there's also unsupervised learning, where the samples from the data are not labeled. For example, you just feed in a rectangle and you just feed in a triangle. So you may be wondering, why do people even use unsupervised learning? Like, what is it useful for? So unsupervised learning is really useful when you want to cluster large amounts of data into groups, because the computer algorithm that you're using in unsupervised learning, like if you use clustering or something like that, it will basically find the differences between the data that you're feeding in. So if you're feeding in a bunch of shapes for image recognition, it would find that the rectangles have 4 sides and the triangles have 3 sides, and then it would cluster those into a few different groups. And that can be really important, especially in, because I come from a biology background, that's really important in protein classification. So that's one application. And then a third type is semi-supervised learning, where some examples have labels and others don't. So as I mentioned, we're going to be focusing on supervised learning during this workshop. And also, if you guys have any questions, please feel free to mute yourself as I go through it. And if I'm going too fast, you can also unmute yourself. I'm so sorry. But yeah, if I'm going too fast, you can also unmute yourself and tell me to go slower. So yeah, there are 2 main supervised machine learning tasks. One is regression and the other is classification. So basically, any task you do with supervised machine learning is going to fall into one of these 2 categories. And regression is where you predict the outcome of a continuous quantitative variable. So that can mean if you want to predict, say, stock prices over certain dates, or if you want to predict sales over time, or if you want to predict age over time, which would be linear, obviously. So basically you're predicting a number which is continuous over another variable. So certain ML algorithms have been developed for regression, and these algorithms are linear regression, neural networks, random forest, or nearest neighbors. So next to neural networks, I have written any DL algorithm. So DL is another subset of AI in machine learning, and it's called deep learning. So neural networks are basically their own little category of deep learning algorithms that are basically connected to each other, and they're formed in network form. So they have multiple layers, and you pass the data in through the layers, and there are weights and biases applied to the data as they pass through the network. So you can use neural networks for basically any application, including regression, and you can also use it in classification. So a couple other algorithms used in regression are random forests and nearest neighbors. So something I'd like to highlight as we move from regression to classification is that many regression algorithms have a counterpart that's really similar, but instead of being used for numerical values, it's used for classifying values. So for example, the classification counterpart of logistic regression would be, of linear regression would be logistic regression, which makes sense because if you imagine a logistic curve, it goes like in this S shape. So it's really good for binary classification. If you want to determine if something is a tumor or not a tumor, if the tire is flat or not flat, or something like that, your values on the top of the logistic curve would correspond to a 1, which would mean yes, or whatever category you choose, and the values at the bottom of the logistic curve would correspond to a 0. So in that way, they're able to categorize the data into 1s and 0s, and that corresponds to binary classification. Similarly, classification trees or carts are the classification counterpart of random forest. So instead of dividing the data by differences in their values, carts do it by differences in qualitative features. And some more classification algorithms are support vector machines, neural networks. Like I said, they can apply to both regression and classification, and also naive Bayes. So we're going to be focusing on regression during this workshop, but classification is also a really cool application of AI, or section of AI, that I think you guys should definitely explore if you are interested. So before we start, I want to highlight an algorithm called, or a theory called no free lunch. So this is a theorem that basically states that there's no single algorithm that is the best fit for a certain task. And what that means is a lot of people think that machine learning engineers know exactly what algorithms fit with what data when they see the data, and they always get the best results on the first try. However, it's actually a guessing check to see which algorithm produces the highest accuracy, because as you saw on this, as you saw on this slide, there are multiple algorithms that apply to both regression and classification tasks. So it's really looking at your data, getting to know your data, and based on that, you should make decisions on what algorithm to use. And as you'll find in the workshop today, not all algorithms work for all data types. So now we're going to be learning linear regression theory. And linear regression is a really good place to start when learning about AI, because it's kind of like the hello world of AI. So whenever people start with like their first AI algorithm, it's always linear regression, because we actually learned it in like 5th grade math. So when our teachers were teaching us about like the slope-intercept form of a line in y equals mx plus b, that can actually be translated to AI, because the linear regression algorithm is actually written in the form y equals mx plus b, because that makes sense. If you have a ton of data points over here, like say this corresponds to predicting the price of an Uber based on like miles traveled, this would be all your different data points. And to predict future data points, what would you do? You would draw a line of best fit, right? So when you're drawing that line of best fit, that's, in theory, it's really easy, but it's a lot harder to find the line of best fit than you would think. So that's what linear regression tries to do. It tries to automate the process of finding the line of best fit. So this is the equation for linear regression. And although it looks like a lot, it just basically means that the predicted y value is equal to a bias, and this bias is set by the model. So that is not a parameter that you could control. It's not a hyperparameter. It is something that the model learns, and it determines that, say, 2 is the best bias for this data. And then it's also, the bias is added to a bunch of features like the x1, the x2, and you can have infinitely many features. So if your data is very multidimensional, there are a lot of different factors that go into it, then you would have a lot of features. However, if your data is two-dimensional and you just have one dependent variable and one independent variable, then your data would just have one x value, so one feature. So the features are multiplied by biases. They're multiplied by weights, which are written over here as coefficients, and in the y equals mx plus b form, the weights correspond to the slope, if you guys are visualizing that form right now. So the weights are also something that the model learns over time as it fits itself to the data that you have given it. So its goal is to try to predict the weights that get you the y value that is closest to the y values that it was given when you were training it. Does that make sense to everybody?
Hello?
Yes.
Okay. Any questions right now? Okay, so I'm assuming there are no questions. So this is basically the mathematical formula of y equals mx plus b, which is also the mathematical formula for linear regression. So if you're looking at this and you're thinking, like, how would I ever code this? Don't worry, because scikit-learn actually has a really great library that you can use to just take linear regression algorithms that have been pre-coded for you, and you can just fit them to your data. So scikit-learn makes it really easy to code in AI, and it's a great place to start if you don't want to reinvent the wheel. And honestly, like, I don't know why you would want to reinvent the wheel and code your own linear regression algorithm. So now let's look into the math behind how exactly we find the line of best fit. Like, how does the model find the bias that works? How does it find the weights that works? It uses something called mean squared error. So this looks really ugly, but it can be summarized really nicely. So if we go back So basically, as I said, you want to minimize it. So let's break it down. So 1 over n is basically 1 over the number of data points that you have. And that is basically taking the average, because if you divide the sum by the total number of data points, that's taking the mean, correct? So that's where the mean part of the mean squared error comes from. Next, you're taking the sum of the differences between the predicted y values minus the actual y values. So if you go back here, you would basically find the difference between this actual y value and the predicted y value of your line for every single data point. So you would add them all up, and then you would square them. So I'm going to ask you guys a question. Why do you think you have to square the differences between the actual and the predicted values? Looking at this. You can just unmute.
Is it because it relates to the y equals mx plus b formula?
Can you elaborate?
No, I'm afraid I can't elaborate any further on that, but it looks like there's a common pattern there.
Okay. Yeah, that was a good guess. But I think it's actually simpler than that. The answer?
Is it to make it more accurate to the actual line? So it's like actually closer to the red line itself.
Okay, but wouldn't squaring it make it go farther away from the red line?
Again, this is just a guess. I don't understand any of this right now.
Okay.
I'm just trying to comprehend it all.
Okay. Yeah, so I'll give you guys the answer. So basically, if you subtract this, if you subtract this point from the predicted y value, you're going to get a positive difference. But if you subtract this point from the predicted y value, you're going to get a negative difference. So over time, these differences all cancel out and they sum to 0. So then that's not very accurate if your error always sums to 0, right? So in order to account for both the positive and negative differences, you need to square them. So every difference is positive and it actually adds on as a difference instead of subtracting from the error. Does that make sense to everyone?
Yeah.
I think so.
Yeah, on the surface of it, that makes sense.
Okay, perfect. So that's what this square does. Basically, it ensures that you're not subtracting from the error, because that wouldn't give you a very accurate representation of what your error actually is. So once you add up all the data points, then since it is the mean squared error, you're finding the mean of that. You just divide by the number of data points, and that is the error. So you want to make that error as small as possible. And our math knowledge tells us that to do that, we would have to make this difference as small as possible, which then the linear regression algorithm tries to make this predicted I minus yi difference as small as possible. So now you may be wondering, well, how does it do that? So you can visualize this formula as a curve. And basically, you start with random weights and biases. Before you fit your data to the model, it starts with random weights and biases. So suppose your error, this is the graph of your mean squared error. So suppose your error is somewhere over here. And that's with random weights and biases. Then the model keeps changing the values of the weights and the bias to slowly move down the curve. And calculus will tell us that, but also like common sense will tell us that like the smallest learning rate or the smallest error will be at the bottom of the curve. So we somehow want to get to the bottom of this curve. And we know that this will happen. Well, okay, but that's like calculus, so we're not going to go into that. But yeah, basically we want to get into the bottom of the curve. So how do we do that? Basically, we're going to take steps, really small steps, which means we're going to change the learning rate in like really small increments. So suppose our weights and biases start off with like y equals x plus 2. So that's our starting weight and bias, 1 and 2. And suppose that gives us an error over here. So now your model is going to try to change that weight and that bias to make that error go down. and it's going to calculate the error after every change it makes to see if it moved down or up. So you can see this thing called learning rate over here, and you can see the difference between a big learning rate and a small learning rate. So before we talk about that, I just want to tell you guys what learning rate is. It's basically the speed at which your model changes the weights and biases. So as you can see, if your model changes from, say, a weight of 1 and a bias of 2 to a weight of 200,000 and a bias of 45, your learning rate would be really big because the rate at which your weights and biases are changing is really large. And with a big learning rate, your model will finish training quicker, but it will also potentially skip over this smallest mean squared error, and therefore it won't be as accurate, even though it'll train quicker because it'll jump all around because it'll be guessing different values. Does that make sense?
Yeah, this looks very similar to me to a sort of a proportional integral derivative control algorithm. So where you've got a function that is trying to stabilize a system. So for example, the SpaceX rocket that lands vertically, it has similar mathematics going on behind it too. It will have a component that tries to minimize error in one direction, but then it will also add another component that is trying to, so it looks very similar to this, but it kind of smooths it out. I don't know if that's the best way to describe it. So you have various different components of the function that are being applied to itself in a feedback mechanism in order to smooth out the response that's required. This looks very similar to that. Is there a sort of a relationship between the two?
Oh, that's really cool. I'm not really familiar with that concept, but I mean, if it looks similar, then, and it has like the same calculus, then I'm assuming like they might be related. But yeah, that's really cool. That's a really cool connection. So yeah, so that's basically the problem with a big learning rate. And the problem with a small learning rate, although it'll move down the curve slower, so it'll have a higher chance of actually making it to the bottom and not just skipping over the bottom. The problem with that is it'll take a really, really long time for it to get to the bottom. So for models with small learning rates, it takes a really long time for them to train, even though they are more accurate. So learning rate is a hyperparameter. And by hyperparameter, I mean that is something that when we are fitting the model to our data, we specify what we want the learning rate to be. So it's up to us to decide whether we want a learning rate of 0.001, which would be a really small learning rate, or a learning rate of 1, which would be a really big learning rate. And we kind of have to weigh the cost and effect of changing the learning rate to make sure that we get the most accurate model with the lowest error, but also that we don't spend like 50 years training it. So that's basically the whole concept of gradient descent. So if you don't get anything else from this workshop, I think gradient descent is a really fundamental part of machine learning because that's like basically the foundation of how every machine learning algorithm works. And I just showed you this in 2D because like it's really simple in 2D to visualize it, but there can be multi-dimensional gradient descent curves as well for more features and also for different algorithms. So does this make sense to everyone?
I think it kind of does. Does the small learning rate, is that a nonlinear optimization? Is that as it's stepping around the curve in small increments? It looks very much like a nonlinear optimization algorithm that's stepping
Yeah.
yeah, like I said, stepping through that curve. I've just been doing some work on that, that's all, and it just looks very familiar.
That's really cool that you guys are finding all these connections. But yeah, so basically it is like following the curve down, but like in this case, it's like following the curve exactly, and it probably won't look like that if you actually visualize a model while it was running. It'll probably like jump around a little bit more, but basically it does follow like the general trend of the curve to get lower to the minimum value.
Thank you.
Okay, cool. So now that we kind of understand, or I hope we totally understand, the theory behind how linear regression works, we're going to try implementing it in our code. So we're going to be doing 2 applications. One will be in stock prices and one will be in business inventory. So one of them is going to work really well with linear regression, and one of them won't work well. So that's where the no free lunch theorem comes in. Like, theoretically, you would think that linear regression would work well for regression data, because, like, theoretically, it would just fit itself to the data, right? But if you think about it, like, inherently, some data is, like, exponential or, like, quadratic. So, like, no matter how hard you try, linear regression is just not going to work for that data. So we're going to see an example of that as well in this workshop. So I'm going to post this Google Colab link in the chat so you guys don't have to like type it all in. And if you guys are experienced in Python, you can just make a copy and delete all of my code, or you can use my code as a reference and try to recreate it on your own. But if you haven't coded before, or if you just want to follow along for my funny comments, then you can just make a copy and then follow along as we go through it. And then the data set we'll be using for one part, you can download over here. I'll also put that in the chat. And this is kind of weird. You need to like upload it to your runtime. So I'll show you guys how to do that from my computer. So I'm going to stop sharing and then post everything in the chat.
I think I'm following everything, but not to the point where I could explain it to someone else.
Okay. Do you have any questions or?
No, it's good. We'll see how much I was following, I guess, on this next stage.
I won't be doing summaries this time, if that's okay. Just, just playing devil's advocate here, my side. I mean, I know all this stuff, right? Why are you laughing, Alex?
Okay, so if everybody could maybe like put one of these on their screens once they're done making a copy, and then also making downloading the Kaggle data. I guess I can just wait until then, and we can like, I don't know. We can. Does anybody? Sorry.
What did you say you wanted us to do once we've done that?
Like post this on your screen.
Ah, the word this. Okay, I was waiting to see what the this was. I'm good at following instructions. Yeah, right, I shall be back.
Yeah, and in the meantime, if anybody like wants to be brave and try to explain like what you did get, I think that would be really good for your guys' understanding, because the first time I learned this, I didn't really get it, but then when I started explaining it to other people, it really helped me like highlight what I did and what I didn't understand.
Okay, should we just walk through that? So for those of us that haven't done this before, you need to connect into Kaggle. Kaggle, I believe, is owned by Google, isn't it, Sui?
Sorry, can you repeat that?
It doesn't matter, actually. It was an off-cuff comment. But so we need to log into Kaggle, but you have a Google login to do that, don't you, if you're already a Gmail user? And then we go in and we download the online business sales, 48 kilobytes, right?
Yes. And
okay.
Yeah, and like know where you download it, because you'll need to access it later. So don't just like download it to like.
Say it again. Could you repeat that, Sue?
Oh, I just said make sure you know like the location where you downloaded it, because you don't want to lose it.
So I'm downloading 48K, right?
Then we go over to collab.research.google.com.
And also for the collab, make sure you guys make a copy, because I think right now it's view only, so you won't be able to do anything.
Okay. So we go to File and Save a Copy. Is that right? Save a copy in Drive, for example?
Yes.
Okay, so do that. And then we need to import that data, right?
Yeah, and once you guys get to that stage, if you know how to do it, you can do it. But if you don't, then I'm going to screen share.
Okay, so far we need to have downloaded the data, got into the Colab screen, and now we're waiting on you to do next steps to import the data. Is that right?
Yep.
Wonderful. How's everybody doing?
I have downloaded and got 2 zip CSV files. Sorry,
Okay.
two files. What do I do with the download? Sorry.
We haven't got there yet.
Yeah, you can just like keep it open.
Wonderful. Then I'm there. Yes.
Okay. Good to hear everybody else is getting on.
So basically, I have like Kaggle is where you put your data, right? So it's just the data that in Kaggle, and then when you go on Colab, it's the code that we will use for where we're gonna put the actual data for the application, right?
Yeah, that's correct.
Okay. So is Colab in this case an emulator for Python, or is it like just like a notepad for Python?
It's like Python, or it's like Jupyter Notebook, but it's, in my opinion, a lot nicer because it's in your Google Drive instead of being on your computer hard drive.
Okay.
Okay, it'd be great to get a bit more feedback here. Everybody downloaded the 2 CSV files successfully in the zip folder. And then ready to see how we import them.
I am, but I can't be the only one.
Okay,
Where are
it was
you?
easy enough this side, but Sam, yeah, great, thank you.
Okay, so
All right, do you want to put your screen back on?
yes, that will be good.
Great.
Okay, so can everybody see my screen?
Yep, it's back.
Okay, so basically you see a screen like this, and you see like 4, I guess, icons on the left-hand side. So if you click on the very bottommost one, that's it's called Files, and it'll take a while to connect to a runtime. So once it does, you will click on this little paper thing with an arrow, and it'll take you to all of your files. And then I downloaded this very recently, so let me see if I can find it. This is why I said know where you download it.
Should we unzip the files before uploading them, or just upload them as a zip?
Ask that, Phil. Great
you have to
question.
unzip.
We need to unzip them.
Yeah, you need to unzip them. Also, I think I deleted it, so just 1 second while I go download it.
Okay, I've unzipped my 2 files. Got the business retail sales and business retail sales 2. Highlight both of them, drop them in. They've come through fine into my files.
Oh, we're uploading both at the same time. Okay, cool.
Okay, so I found them, and now I will continue sharing.
Alex, you getting on okay? Great.
Okay, can you see it? But this is a Kaggle thing, right?
Just
Okay.
see one taskbar here, is that right?
Sorry?
We don't have this.
We've got 1 bar, that's it.
That you can see?
Mm-hmm.
Okay, but you can like see my Google Colab, right?
Not really.
Not really, no.
Oh, okay.
Do you want to just try again? Start and stop.
Oh, okay, there we go. I was sharing the wrong thing. Okay,
Perfect.
so everyone can see it now?
Mm-hmm.
Yes.
Okay, perfect. So now you go to Files, and then you, okay, and then you go to mine is saved under Archive, and then you'll see 2. You can just pick like whichever one you want. I'll just pick the first one, and then you just choose it, and that means it uploads to your runtime. And this just means when the runtime is recycled. So if you close your computer and you go away, or if you lose your Wi-Fi connection, you will lose these files as well. So every time you open up this document, you'll have to re-upload the files, or else you'll get errors. So that's all that means. So then you'll see over here that it has been loaded into your runtime with this name, .csv. So mine is uploaded under this name, but if you have a different name, then take note of that, because when we read the data and kind of put it into our linear regression algorithm, you need to get the name right, or else you'll get an error. So is everyone good with that?
Yes, I have one question though, because you've only uploaded one file and I've uploaded 2 files. I'm just checking that I've got business retail sales and business retail sales too.
So I think they're the same file. They're just like copies for some reason. So you can like choose whichever one you want.
Zoe, I've got mine like yours.
One's larger than the other, possibly.
Oh, is it? One's got more data in it.
Yeah.
So I'm just going to delete all the results.
Yeah, one's a lot bigger,
Well,
actually.
do you want the one that is per month, or do you want the one that is per product?
I want the one where in the 0th column there is product name.
Okay, so art and sculpture, basket, art and sculpture. Yeah.
Yeah.
Okay.
So it's the one that is without a number then, Bridget.
Yeah.
Thank you. The larger size file then. Cool.
That's right.
Thank you, Nina.
You're very welcome, Bridget.
Okay. Everybody ready for us to carry on?
Yep.
Okay, perfect. So in every Python project, there are going to be some libraries that you just cannot get around importing. So like you'll probably memorize them if you continue coding in Python. And these libraries are NumPy, so I'm importing that as NP. And this really helps with performing high-level array tasks. It makes it a lot easier. You also have to import pandas as PD. And this is a data analyzation library that lets you convert data into really nice tables that are very aesthetically pleasing. And then also matplotlib.pyplot as PLT lets you visualize your data, so lets you create really nice looking graphs, change the color, which I love doing, creating or graphing your line of best fit. So that's really good in visualization. And then sklearn, as I mentioned earlier, is where as a beginner you can get really nice machine learning models from without like basically any code. So from that, we're just importing the linear regression model. And then since we're doing 2 applications, in addition to this business retail one, we're also doing the stock data. These 2 are specific to just the stocks. So whereas these you're probably going to import every single time, these 2 are just specific to this one workshop that we're doing. So this is importing datetime as DT, and this library basically makes it really easy for us to store data in terms of date and time values. And this is helping us read the stock data that we're taking from the web. So we're going to do the stock application second. So first we're going to start with business retails. So I'm creating a new data frame, which is what this df means, and I'm using pandas to read this CSV file that we just uploaded. And in my thing, it's called business.retail sales. So I just put that name in exactly how it was over here. And make sure you write it as a string. So does everybody know what a string is?
No.
Okay, so no worries. A string is just, I like to think of it as dialogue in a book, where because it's like words, and the words have to be placed together in a certain way, you put quotations around it because it's kind of like you're talking in the code. And the difference between strings and other data types are, for example, like this would be a variable, and you don't put that in quotations because it's like not talking. Do you know what I mean?
Yes.
That's how I think.
Yeah.
Okay.
I have another question. Sorry. Can you, I don't know what array tasks are. Right at the beginning, you said import NumPy as NP.
Oh, so that's just basically like if you're doing anything with an array, like if you're deleting values, if you're adding values, if you're reading values from an array, NumPy just helps with that.
Okay, thank you.
Okay, so now we're going to look at the first few columns, or the first few values in our data set. So I'm just going to run this code. And, oh, I need to run this first. Because you need to run everything in succession because I declared PD over here. So because the computer didn't know that I had declared it over here, because I didn't run it, it gave me an error. So you can see that I'm getting a really nice table thanks to pandas, and I can see the net quantity of the products, the gross sales, the discounts, the returns, and the total net sales. So I was just trying to make this as simple as possible, and I don't think like people actually do this like in business, but we're just trying to predict the total net sales from the net quantity. And yeah, like if anybody like is actually in business who like does visualization or like prediction models, you can like tell me if like you guys actually use net quantity to predict net sales. But I don't know, like I thought that would be a cool I guess relationship to kind of predict. So I'd also like to highlight, if you haven't, your table might look a little bit different from mine. Actually, it won't, because I put this into your code. But this basically means that there was a column called product type. So if I comment this out and I rerun this, you'll see there's a column called product type. But that is problematic because our code can only take integers or doubles. Double is basically a decimal number and integer is basically a whole number. So our code, the linear regression algorithm, like I said, is quantitative. It predicts quantitative values. So it only takes numbers. And these are words. So they're not going to work out. So that's why we have to drop that column in order for this code to be run through, or in order for this data to be run through our algorithm. Does that make sense?
Yep.
Okay, perfect. So now we're going to pull all the data from the net quantity column, because like I said, we're going to try to use the quantity to predict the net sales. So this just shows the data, and you can see how this is actually the data taken right before and then during the coronavirus pandemic. So you can see this business was impacted pretty harshly by the pandemic in that their sales dropped from, or their quantity dropped from a lot to like very little, which suggests that, you know, they had a lower quantity because they weren't selling as much. So yeah. And then we're basically reshaping the array between -1 and 1 just to make training the model a lot faster. So I just printed X so you can kind of see what it looks like. And by reshape, I mean the array was reshaped from -1 to 1, so there are still values that are not -1 and 1. So this is really important over here. This is where we're actually fitting the regression algorithm to our X and Y data. So before, this was all data preprocessing. And because our data is so simple, and it's already fairly clean, all we needed to do was just drop that one column that had strings in it, and then our data was preprocessed. But in real machine learning tasks or projects, you can spend months on preprocessing. Like I'm completing a project right now where we're doing, where we're labeling anatomical features from MRI images, and I think I've spent 4 months on data preprocessing and I'm still not done. So like that's kind of, you spend a lot of time on data preprocessing basically is what I wanted to say. And yeah, so, and we were just visualizing the data, getting to know it, and trying to like figure out what algorithm would maybe best predict what we're trying to predict. And then over here, we're just declaring our X and Y values. So this X value is basically every single column, and this Y value is the net quantity. And now that we have our X and Y values, this is where we're fitting the linear regression algorithm to our X and Y values. So, wait, this is a spoiler. But so if you run that, your model will fit. And then to get the score or how well the model did in terms of accuracy, you can press play. You can see that this model is not very accurate. So, I mean, you guys can all say this, but like, why do you think the model isn't very accurate?
Is it because there's an external, you mentioned the pandemic, there's an external influence that may be affecting the data that's not, you can't necessarily derive the result from the, from what the inference is incorrect based on the starting point.
Yeah, that's actually exactly right on. And that's like the same reason why the stock data that we're going to be doing later wasn't as accurate as it should have been because of that dip caused by the pandemic. So you can see that like over here, the initial value was very high, but then because of the pandemic, instead of being linear, this inventory literally became like an exponential curve. And like I said earlier, linear regression just doesn't work when your data is shaped like an exponential curve or like a quadratic curve. So it did the best it could, but as you can see, linear regression was not the best fit for this data set.
So you said that the score was not accurate. What is an accurate score?
So my threshold is anything over 50%, and I would say that because 50% is like the chance that you have when you're guessing, like 50-50, you either get it or you don't. And if it's lower than 50%, that means like it's worse than random chance, and you want to be better than random chance if you are making an ML algorithm. So I would say better than 50% is desirable, and actually better than 90% would be best because then it actually is predicting what it's supposed to predict. Otherwise, it's just guessing and checking, and like that's not really what we're trying to do.
And so 0.206 is 20.69%, right?
Yeah.
Thank you.
So it's like even lower than just guessing and checking.
So we're trying to find a function effectively that best matches the data that could be then used to describe where ongoing data points are likely to lie in the future.
Yeah, exactly. And we're just making the computer do it for us instead of like doing it on our calculators or something. So then I tried predicting, instead of net quantity, which I predicted up here, I tried predicting total net sales, and that is a spoiler. So I'm actually going to, well, okay, I already spoiled it for you guys, but basically I wanted to delete this code and ask you guys to code it yourselves because you've already seen it over here, but like it's already written, so sorry about that. But yeah, so if you run it, then you see that the regression score is like just as bad because the data set itself is just very curvy and linear regression does not work. So, but do not be alarmed or disheartened because we have a data set that'll work a lot better with linear regression data because it's a lot straighter. So yeah, so that's going to be our stock data. And like I said earlier, this isn't going to be as accurate as we want it to be because of the pandemic, but it's still going to be pretty accurate because the pandemic only dips at the end. So yeah. So basically, this is really cool because we're going to be using datetime to read stock data straight from the internet. So we're going all the way back to January 1st, 2016, and taking stock data from the S&P 500 from Yahoo, and that's going to be our data set. So if you just press play on this cell, then you can see, by the way, this is like October 2020 because we brought it to today. So that's why that is showing really recent data. So you can see the highest point, the lowest point, open, close, and volume adjusted close. So like
this is from the internet, so it has nothing to do with the database that we imported, for example.
No, it does not.
And okay, so I have an error every time I do something. So when you press play, you have something, but when I press play, I have this says that my pandas are not defined. So basically, I have an error. Trace back most recent cell last name. Yeah.
If it says PD is not defined, make sure you ran this.
When
cell.
what?
I wasn't. Yeah, I wasn't sure either. So I'd run the first part of the from the top, and then I get the same thing actually. Traceback most recent call last key error.
And is it because you put the hashtag when Suri puts the hashtag as well?
Oh, this?
No. So at the beginning, when you were on the first square, just after the import bit, you have like df equals df.drop columns equal product type, and you put an hashtag in front of it at some point. And I did the same. And once I did the same and I ran it, yours did something and mine completely like crashed. So basically right now, the pandas are not defined. So is it because I killed the relationship between the database and the code, or?
So when I put a hashtag over here,
Yeah.
I basically commented out this line. So when the code was running, it just skipped over this line. But I don't think that should affect anything.
Okay, so yeah.
Because like this is regarding this file and the stock data is taken from the internet.
Okay, so mine is not working.
Okay.
So let me just pop my screen up for a second.
Yeah.
Just check if I'm getting the same thing here. So let me just see if this is similar or not.
It seems to be working for me.
Oh, that's good to hear. Okay. No, there is
It's possible.
Well, that, yeah, it's all right. But point taken, by the way.
Also working for me.
I have a different one.
To be honest, I'm not sure what I did right.
So
maybe if I rerun the top.
Zoe, is there something I've missed off this?
Oh, so I have now the same as you. So I run the line, I think it's line 14 or something else, and so box 14, and when I run it now, I think I have.
Okay. Well,
Yeah.
Richard, I know what you did wrong. So basically, when you're defining your df, it's not defined because this is like this over here. No, above that. Like below that. In between your two code boxes, your df is as a text thing, but that's why it's not reading it because the Python doesn't read the text. That's just like for you. So you just copy and paste that right above your plt.plot.
I copy and paste this.
In cell 15.
You want me to pop this in here?
Yes.
Like that.
Oh, wait, so you deleted what was there before. So if you can, yeah, okay. And then just enter it above that. Okay, and then you can see that you have commands going, or multiple commands on the same line, so that's also going to give you an error. Yeah, it says invalid syntax. So if you just press enter between the different commands and put them all on their separate line, or if you put semicolons between them, that'll fix that problem.
Okay.
So basically after this business.retailsales.csv, press enter. And then after df.head, press enter.
Here.
The first df.head.
Here.
Yeah. And then after oh, also you don't have to run it after like every time you do something.
Yeah, okay.
Okay. And then after the product type, you can press enter. Okay, that should work.
Okay. There we go.
Okay, so I think I found what I have. So your plt.plot is not at the same box as mine. So should they be on the same box?
Yeah, and
okay.
If you do the same thing as Richard, where you like accidentally made it into a text file or like a text box, just copy and paste that into your code box.
Okay. No, I didn't, but it's fine. I can just like copy another collab, make another copy of the collab, and I'll check what was wrong.
Okay, sounds good.
Thank you for making that mistake, because that was a good learning experience.
Yes, yes. Thought it'd be helpful if I did that.
Yes, I appreciate it.
Okay, so if we continue, can everyone see my screen?
Yes.
Okay, perfect.
Yeah.
So does everybody see?
Yes. Please.
Sorry?
Yeah, I just want to ask a question before you continue.
Yeah, of course.
May I know at the end if we can access the recording?
Sorry,
How can we access the recording at the end when we finish?
Oh, the recording?
Yeah,
I think you'll ask Richard for that.
Yep.
Yeah. So it does take a few moments to download and then upload from Zoom, so it won't be straight away. But I'll put it up probably about 3 hours after the meeting on our website, which is MKAI.org. I'm going to put it here in the chat for you, and you'll see it in the learning resources part. You can't miss it. It's on the header of the website, learning resources, and we'll pop it in there later on tonight. Is that all right?
Okay, thank you.
My pleasure.
Okay, so are there any more errors that we need to go over?
I'm good, thank you.
Okay, perfect. So now that we can see the data, the stock market data, we are basically going to pull the data from the adjusted close column. And I know nothing about stocks, so I assumed that the adjusted close column would basically be like the price at closing, but like adjusted for inflation. So correct me if I'm wrong, but like I thought that would be like the most accurate representation of where the stock market was at. So that's why I chose that. But if you want to choose any of the other columns, like feel free to. I don't know if volume would be very helpful though, because like I don't know what that means, but yes. Okay, so if we pull from the adjusted close column, you can see what the data looks like, and you can see at the beginning of 2020 how there was a big drop in the stock market, but then it goes back up. So does everybody see this?
Yeah.
Okay.
Yeah.
Perfect. So now we're going to assign values to our x and y variables, just like we did in the first example. So can you guys, I guess, try not to look, and can you guys do it yourselves? And then also, like, it'll be here if you need to look.
So, no. Let me go back and have a look and come on unmute for a moment.
Okay. And if you can't, like, this is like the right answer. So, and I think you guys have it like in your notebook as well, because it just copied over. But if you guys like want to challenge yourselves, you can delete that answer and try to recreate it yourselves.
I think there's also one thing is having familiarity with Python, but another thing is having familiarity with the API of the particular library that's in use. So it might be possible, but without looking up the function, it might be tricky to guess.
Yeah. Yeah, that makes sense. That's why, like I said, I tried to like have the code there for you guys, so like no one's like super confused.
Yeah, it's helpful.
That's good. I'm glad. Okay, so if everybody has given it at least a thought, we can go over like how this breaks down. So basically, we are, oh, and also something really cool about Google Colab is if you like hover over certain things, you can like get the definition of them, so, and like certain documentation and stuff. So I think that's really cool if you're ever not sure about what to do. So anyway, so for the X data, we are trying to look at stock market data over time. So the independent variable is going to be time, because you can see it's on the x-axis. So we're basically using NumPy to arrange the values for x from 0, which in this case 0 is when we're starting. So we're starting at January 1st, 2016. And we're just reshaping it from -1 to 1, so it looks nice. That's just like, it's kind of like, it's just like a cosmetic thing. And we are doing it for every single value in the data frame for dates, so that's why we're doing df.shape 0. So for the y value, we want to predict the stock data. That's the dependent variable, so that's why we are just taking the entire data frame for adjusted close, so this entire column, and we are making it nice and accessible using NumPy, so that's what the 2NumPy is for. So that just loads our variables up, and you can run that. And now, like we did up here, I love how easy they made it, because you just say linear regression dot fit, and then you just put your data in. So you can fit it, and your regression variable, or your regression model is going to be called regression. You can call it like whatever you want, like pink unicorn panda, but I would say like make it descriptive of what it does. So yeah. So then you can run that and fit your data to the linear regression model and create your model, and you can see your score. So you will see the score is significantly better at predicting the stock market data over time, because this model has been trained very well. So I'm not going to give any financial advice, because I also don't know anything about finance, but if you guys, and also like I don't know about investing, but like if you guys wanted to see or predict or try to like just try to see like where a stock price would be going in the future, and kind of use that as a tool. I'm not giving financial advice, but if you wanted to, you could definitely run the same algorithm on individual stock prices and see like if they continue going up, how much are they going to go up? It's not going to be very useful for sudden drops, because nothing can predict the stock market, but yeah, if you want to see like steady growth, like how steady is it going to be, like where is it going to go, you can use linear regression to predict that in the future, barring any like external effects or events like coronavirus, like Phil said.
So it's quite dangerous to use right now then.
Yeah, like right now, don't use it. It won't be very accurate. But, well, actually, it was pretty accurate. But that's just because like the S&P 500 is less volatile than like individual stock prices. But yeah, like you do you. Like this is all at your own risk, I guess. Don't like put any money behind it. I don't know.
We did an
But yeah, and then if you want to print what your model.
Yeah.
Sorry?
It's not. Excuse me. I've just changed the where it takes its information from the adjusted close to the close, which are the exact same units, but it's come up with a different answer than yours. Why is that happened?
For the regression score?
Yes. I've taken it from closed instead of a just closed, but they're the exact same values. So, but I've got a different regression score.
Okay, well, there are two explanations for that. First of all, although the adjusted close, if my prediction is right, where adjusted close is adjusting for inflation, then although the values are the same for this df.tail, maybe if you look at the df.head, we can actually try it. If you look at df.head, maybe they'll be different.
Zui, I actually have but I just re-executed the each of the lines. So I actually put in the chat that I returned a different regression score previously, but I'm now back on track.
Okay, perfect. But yeah, but that was like a really good point that you made, because although the adjusted close values are the same as the close values in October 2020, they are different than the close values in January 2016. So that might also contribute to a difference in the regression score. But then also, like we're training this model live, so and it's random, So basically the random decisions that my model makes is going to be different from the decisions that your model makes. So there might be slight variations, but if you get like a 40%, then that is a big difference.
Okay. Okay, and thank you.
Yeah, of course. So this is just like me playing around now. I just wanted to see if we could write it in y equals mx plus b form. So if like we were in math class and we needed to like predict it in like 2024, barring any like sudden pandemics, we would be able to. So this is our m value and this is our b value. And now I am good and I will be able to get an A on the test if I was predicting it. Yeah, that was a joke. And then
We're laughing. We got our mute buttons on.
okay.
I was laughing, Louis. I got it.
Thank you. And then this is basically where we're just graphing our line against the graph of the stock market. So you can see that it is actually pretty good, except for like this little dip here. Like if this had kept going up, our line would have been like really accurate. So yes. And I really like graphing in Python, so I'm just going to go over a few specifications. So over here, you basically put in your x values and your y values, which we defined over here. And as you can see, like the y value is our line. So that's what the y function means, and it's the m times x plus b. And this x is basically all of your features. So it's a NumPy array of everything, every data value from 2016 January to October 20th, October 19th, 2020. So that is what that is. And then you graph that line over here. You can make it whatever color you want. I really like pink, so I made mine magenta. You can make it like red if you want. And yeah, and there are like a bunch of other colors, but I keep forgetting like what the abbreviations are. But if I like put in a color that like wasn't valid, it would just give me an error. Or okay, this is weird. But yeah, so you can play around with how it looks if you want to make it pretty, but I like magenta. And then you can also label it whatever you want. So I'm labeling mine linear regression because that's what I want to call my line. And you can decide where to put your legend. So I only have one thing in my legend, and I want to put it on the upper left corner. So I said it's going to be in the upper left. And yeah, and then you just plot it. So that is pretty much it. You guys have successfully made 2 machine learning algorithms. One was a lot more accurate than the other. And hopefully you guys can use what you learned today and build on it if you want to, but also you'll be a lot more informed about what AI is, where you can apply it, and if you ever wanted to play around, you have some code that you can jump off of and refer to.
Fantastic.
Thank you.
How was Sam's score, by the way?
Sorry?
Sam posted his regression score. How does that look?
Was that for the stock data?
I believe so, yeah. Just a few moments ago.
Okay, that's like very low. So you might be predicting the wrong thing. I'm not sure.
Okay. So are you wrapping up, or are you ready to take some Q&A? What would you like to do?
That was all of the content I had. I do have another slide in my presentation, so I can show that. But after that, we can just do Q&A. Or if you guys want to go over certain parts of the presentation that maybe I went too fast over, like it's up to you.
Okay, well, let's start by doing that and open the floor up and just seeing how we all did. Okay, so
The question. Oh, sorry. Talk over someone else.
No, go ahead.
I was interested, your linear regression line plotted to the end of your data set. Can you plot beyond in a predictive fashion beyond your data set?
Yes. Okay, so if you go, can you still see my screen?
Yes.
Okay.
Yeah.
Okay, so over here, it plotted to the end because we told it to only go up to df.shape, which was the end of the data set, but you can also extend the legend to go farther than that, and it would. So yeah, you can do that.
I just think that would be a really cool addition, because your real value of linear regression is the ability to forecast.
Yeah. So that would be good.
Is it easy to show us what that looks like?
Yeah, so actually I'm not really sure how to, I would have to look on Stack Overflow because I love
Sure.
Stack Overflow. But yeah, but if you guys want to ask more questions, I can look really quickly and we can see if we can do that.
Thank you.
I had a question for you, which is quite a personal one about you in terms of what it is that you hope to achieve with AI.
Sure.
So yeah, what are your ambitions? What are your intentions for how you want to put these things to work?
I mean, short of being a stock market extraordinaire, what is it that you as a young person see the value of, and what is it that we, what is it you think that we can really achieve?
Yeah, so as I said earlier, I'm really interested in the biological side of AI, mainly because I'm very interested in studying aging and human longevity. And initially, like when I was younger, I figured that I would become a biologist and just like do a bunch of experiments by hand. But I figured that would take a very long time once I learned that there are over 3 billion base pairs in the human genome. And I'm pretty lazy, so I was not about to go through all 3 billion base pairs and try to find like, certain genes that corresponded to longevity. So that's when I tried looking into how to automate it. And that's when I found out about AI. And initially, I didn't like realize that you could use it in bioinformatics, which is what I'm really interested in. I just thought it would like Siri and Netflix and Spotify were like the only ones who could be using it. But once I started looking into it, I learned all about like I mentioned, clustering algorithms and how you can use intrinsic and extrinsic searches to find certain genes that can be related to certain functions, certain proteins that can be created that can have the information that you want. So I became really interested, and so then I just started learning as much as I could. I taught myself Python, and also I taught myself AI through like online courses and stuff. And I'm currently using my skills in the realm of image recognition with, like I mentioned, stroke analysis. So I'm currently working on a larger project where we're basically trying to make it as easy as possible for radiologists to conduct intravenous imaging and also intravenous thrombosis removal. So my part of the project consists of labeling anatomical features in images, and that is also a really cool experience. So like I said, initially I was interested in longevity, but now I'm really interested in also the imaging side and kind of how you can use AI as a radiologist. So you can like be an interdisciplinary kind of professional. So like my research mentor, actually, he's a doctor and he does actual interventional procedures, but he's also like developing the very algorithms that'll help him one day in doing these procedures. So I just think like the whole intersection of that and how you can use it to help in research and also to help like actual humans is just really cool.
I think Zoe and I have a different definition of lazy. That's incredible. So I don't want to be the dunce of the class, but it would help me if we could kind of go through the coding again, because I know that you said you don't have to write your own code, that you can take it from the library, but it would still be, I think I'd still like to understand a little bit more of what that code looks like. So if I did want to copy and paste and edit, I would have a better chance of being successful.
So like just go through the coding portion again?
I would like that, but if I'm the only one, I'm, you know.
Yeah, I mean, it's fine with me.
So just before you jump back into that for a second, Zoe, I'm going to pop up the next event in the chat here, URL to Eventbrite. So I won't interrupt, but I'll put that up, and you can see a bit about what the next session is going to be and when it is. So if you want to click on that link and get yourself registered for that, this is a great chance to do it.
Thank you.
But back to you to reinforce some of the learning. No pun
Perfect.
intended.
Yeah,
So was that funny?
That was funny.
Okay, thanks.
Okay, so we can start at the beginning again. So, well, okay, so how do you want to do this? Like, do you want me to like go through it again, or do you guys want to, I guess like unmute yourselves and explain what you got from the first time, and then I can fill in the holes?
Could we see somebody doing it? Maybe Sam, would you want to pop your screen up and we'll just learn from seeing somebody work through it as well? Don't let me put you on the spot, Sam, but somebody perhaps, or Alex, would be willing to maybe show us what they're doing? How would that sound?
Do you want me to share?
I don't want to put anybody on the spot. Sam says he thinks he can show, so
Okay.
you know.
Yeah.
Sam, you should have screen access if you want to pop yours up.
Hello? Does that work?
That's good. Yeah, thanks, Sam.
If I go up to the top, I don't know how I've kind of made it change as I go through. Like, I just did like running it once again, and as I go through, it just changes the score. I don't know if it does it every time. I did like a couple times, and it did just change. For the most part, what I'm kind of just trying to understand is just the whole thing is what it does, and maybe as it goes on, just kind of the in-depth different parts of it, because I understand some of it, but there are some parts that make my brain start to fry.
Okay. So, well, let's address the first question. So basically, when you rerun it, your regression score changes because, like I said, like you're retraining the model. So maybe it'll train better, maybe it'll train worse.
Yeah, as it goes on, it'll read differently depending on how it thinks it, like the data it shows.
Yeah.
Okay. So maybe, because I know the importing part, so maybe as we go along, just kind of giving a brief detail of what stuff does might help.
Okay.
So like, as we get to like the DF reading parts of what that does, I think I can kind of understand what that does. It's just reading through the file we ported in and then just pastes that into this box here, while we removed one of the columns because that is a string and not an integer.
Yes, exactly. And df.head is the function that allowed us to see the first few values of the CSV file.
Right.
What does df mean?
Data frame.
Okay. So that's the CSV file is the data frame in this instance.
Yeah.
Okay.
And then this next bit here, the like data form here we've shown, this is pretty much all it does. It just turns what we've got, the numbers, into this table, right?
Yeah, it just lets you visualize it as a graph.
Okay. This part here I think might stump me a bit more. I just need a basic rundown of what's going on here.
Yeah, so basically, over here, we are looking at the x values. So the x values are basically I guess the values in the CSV file. So you can see that they go from 0 to 1774. So that means there's or in your case, there's 1207.
Okay.
Or yeah, there's 1774 entries in the data table, and we're just reshaping it. Like I said, it's just more of a cosmetics thing, so when you graph it later, it'll be a lot nicer to look at. And so this is basically an array of all of the x values because we're just trying to predict the net quantity over time in this part of the workshop. So the time that we're kind of using is basically just every single entry, which isn't like the best measure of time, but like I think that was the closest thing we had. So basically these are all the time values in the data frame.
And you've said before in the last one, the stock markets, that you put in 0, which means all of it?
Yeah, so when you do df.shape 0, that means the entire whatever it is. So since we're just doing like the 0th column, that means the entire 0th column.
Okay, and if I wanted to just use a subsection of the data frame, what would I put in instead of 0?
Then it's indexed, it's 0 index. So if you wanted to view like, say, the net quantity column, you wouldn't put 0. You would actually put the title of the column. So you would say df and then in brackets the name of the column that you just want to index.
Okay.
Yeah. So 0 is just the first column, 1 is the second column, 2, and then presumably you can use the name alternatively.
Yes. And I've actually never used the number. I've always just used the name.
So for the regression equals linear regression part, could you give me a brief understanding of what's going on there? Because
yeah. Oh, actually, do you want to like click on that again so we can see the, or no, so we can like see the Google Colab kind of blurb?
which one you want me to run?
Just
highlight over linear regression, put your mouse over it.
Oh.
Okay, so basically, this does a really good job of like telling you exactly what goes into the function. So you can see if you go up a little, if you scroll up a little bit, you can see that linear regression is the function that was created by scikit-learn, and basically you don't need to specify all of these values because they are assumed to be true, false, true, and none. But that's why like you can just make the parameters thing empty. As you can see, after linear regression, you just have 2 parentheses without anything in them. If you wanted to change any of these parameters, then you would like say fit intercept equals false, but I don't know why you would do that because you want it to fit the intercept. So that's what that means. So basically, it's a linear regression function that takes in the parameters fit, intercept, normalize, copy, and end jobs, and these are all Booleans. So you only get 2 options, and the best options are the default options. And then you are fitting this linear regression function to your x and y values. So you're using the x values to predict the y values according to the linear regression function parameters.
All right. And then the regression score is just showing kind of what the AI has gotten from the data you've given to it.
Yeah. So yeah, basically. And it's, you can use .score because it's like I think it's, I don't know the technical name, but I think it's like a property of the linear regression algorithm that you downloaded from scikit, or not downloaded, that you took from scikit-learn, imported.
So just to get this right, so the score that we get is between 0 and 1,
Yes.
and it is how well the data fits a linear function effectively when scaled to the data set that's provided. Is that right?
Yes, exactly. And you want to be closest to 1.
That's nice and clear. That's good.
Oh, so you actually did better on this one, so congratulations.
And then on the bit here, it's just going from Yahoo, showing the data that it's getting from there in the most recent format. and then
Yes.
goes down and takes that data and puts it into a chart again for us, right?
Yes, but if you wanted to show the oldest part of the data, then you would say df.head instead of df.tail. Does everyone like get what that like reference is? Because I thought it was weird at first, but then I realized like head is like your top, so like that's like the earliest, and like tail is like, well, we don't have tails, but like tail is like the back, so that's like the most recent.
Yeah, so the beginning or the end of the data set, so you can sort of preview that in the table if you just want to look at it. But DF contains all of the data. It's just that it's not showing it.
Yeah, because it's a lot of data. Like that would be so many values if you're, because that's like 4 years of like every single day there's a new entry.
Yeah, and just on that linear regression function again, presumably the point there is that you're not necessarily specifying what the formula is that represents that line, but what you're trying to see if there is a line there somewhere and how well it fits that line. Yeah.
Yes, because the formula and all, like, you know, that really big error function that I showed you in the presentation?
Yeah.
And then also the y equals mx plus b1, b2, b3, all of that I showed you in the presentation. So the scikit-learn basically makes the error function help the y equals mx plus b part of it become more accurate when it's guessing. And since that code is tedious and long, it does it for you, so you don't have to do it, and you just take it from the library and you use it as a linear regression function.
Great, thanks. That's good.
Would you mind if after that I share my screen to see if we can debug the code? Because it never worked for me to run the thing, and I've made another copy of your file, but still wasn't doing the trick.
Yeah, of course.
Cool. Okay, so can you see my screen?
Yes.
Okay, so basically, so my file is here, the one that I imported. I have a second one I didn't do. The imported is this one here, but we're only using this, the one here, right?
Yes.
Okay. So basically, when I run that, I get this error here saying that the name PD is not defined. So I guess the data is not defined where it should be, where my data frame here specifically says that I should use that. So I've checked the name of the file. It seems to be the good one.
Yeah, so your name and everything is right, so you don't have to worry about that. I think, have you tried running the first cell? And then run the second one.
Oh, okay.
Yeah, so basically why that is the computer is basically blind. So if you don't run everything in the order that it's supposed to be run in, then the computer won't know that like this code cell exists. So
okay.
It's undefined.
So now it's going to be working for everything.
Presumably, yeah, because well,
I need to run everything in order, so I need to rerun everything that I've run already.
Or what you can do, if you don't want to like individually press everything, you can just go to runtime and then run all. And it'll run everything in order for you.
Okay. Brilliant. And does everything needs to be in CSV, or can it run as well data that is, so can you basically run data from a scrap website? For example, I have a website, I want to extract the data, it's an HTML, then I have to transform the HTML into a CSV and import it in there, or could it do it with the HTML and me qualifying the data inside Colab?
Well, okay, so can you elaborate on what you would do with the HTML?
So extracting data from a website in an HTML file. So, okay. Yeah.
Yeah, so I've never done that.
Okay.
I'm assuming you would be able to, like, I'm not sure why, as long as it's in tabular format, like, it wouldn't be able to just take, like, straight text. So you would have to, like, make sure it's tabular, but I'm assuming like it would be able to.